Hello and welcome back to another video with It's Dr. Dan, and today we're going to be learning about acid-base titrations. And specifically, we're going to learn all about how to find the concentration of these different solutions when you are trying to mix them together. Now, with these, the whole idea here, what we're trying to figure out with concentration is we are doing molarity. So, what exactly is a titration? Let's start with the basics. So, generally, what it is whenever you have, let's say, a burette, which is this long piece of glassware over here, that's a very accurate piece of glassware, and you're trying to control how much solution you are reacting, let's say, with another vessel. So, in this case, I have an acid with an indicator in this Erlenmeyer flask and a base up in this burette up here. Now, one thing that what exactly are we using this for? Well, it's generally used to determine the unknown concentration by reacting a precise volume of solution, such as an acid in this situation, with a precise volume of another solution, such as a base. Now, the thing that's different is the other solution, you know the concentration. So one of them is unknown and the other is known. And the whole idea here is you're trying to figure out the exact point where they neutralize each other. So that way you can get ideas of maybe what the equivalence point is when the concentrations are equal to each other, how exactly the acid and base behaves. It gives you ideas about concepts known as equilibrium, about pH, how exactly a buffer could work, which is another acid-base concept, is a very widely used concept that is used very regularly in chemistry, in the health sciences, and biology, where we're really trying to focus on acid-base neutralization. Now, what exactly does this refer to? Just to kind of as a little reminder, is acid-base neutralization is a double replacement reaction. So it's a subtype. Now, specifically, neutralize means that we're taking out the acid and the base characteristics, which are extremely dangerous. Now, how do we take them out? Is we can make salt and water as a product to help take those out. Okay, so we're measuring essentially the loss of acid, the loss of base. So whenever we're looking at these, as acids always have H plus as its main characteristic, and bases always have OH minus. So when we add these two together, we're always going to be making a happy water molecule as a result. So let's take a look at a little bit more about the vocabulary behind this before we solve a couple problems. So the biggest component here is that we are going to be doing something like this in the lab, meaning that we'll need a couple important pieces of glassware available to us. So typically we're always using a burette and a flask together. Now the reason we use a burette is that we can actually very accurately control this flow knob here to be able to flow out liquid at any rate that you choose, whether it's really slow, very fast, but it's very precise. It goes to a very high number of decimal places. It's one of the more accurate and precise piece of glassware that we have at our disposal. The other thing that we'll use is an indicator, which is commonly used in biology and chemistry to denote when a chemical reaction occurs. So what an indicator does is that, well, it indicates when this happens via a color change. So it's something that you can perceive easily in the lab without needing any fancy equipment. Typically, it takes advantage of pH changes or maybe if a particular product is formed. So that way you can actually tell, like, oh, this happened. It's very readily used in microbiology as well as in chemistry, and even sometimes in physiology to determine different macromolecules as well. So when we are using these, the whole idea here is being that we have, let's say, HCl, which is on the left-hand side, and we don't know what its concentration is. Well, we can essentially figure that out with a very specific concentration of base, which we have 0.100 molar base on the right of that. So when we're using those, we will add those two together. And the whole idea is we are going to be adding base very, very slowly. Now, as the pH changes, which we'll talk about in future videos, eventually this indicator is going to change colors when the pH reaches that neutralization. Now, when we add base very slowly, what's happening is, remember, H plus and OH minus are combining to make water. And the H plus is going to keep decreasing, decreasing, decreasing as we're going. So it's going to keep progressing forward. Now, at some point, when will all of a sudden it flip like a switch and go from one to the other? This is where the equivalence point is, meaning where the concentrations are equal to each other. When can it go no farther? And it's going to turn pink in an instant. So this is when it goes from acidic to basic. And this is known as the end point. So where do you stop the reaction, right? So generally it's right after that equivalence point was reached is when you stop, whereas all of a sudden you have a little bit more OH minus than H plus. And this is something that we're going to be doing in the lab in the future. So this is the whole idea of what these types of reactions are and how to calculate them, is exactly what volume or molarity is required to neutralize these different solutions. Let's go back to our practice problems. When you're in lab, sometimes you write really quickly and you can't read the notes later and you don't know exactly what it is. Well, this could be something that's very dangerous, especially when it comes to acids and bases. So we want to know what the concentration is so we know exactly how to handle it. So what could we do to do that? Well, this is when you can perform an acid-base titration. And what we will do is we're going to place 20 milliliters of the HCl in a flask with an indicator. And what we have on hand is we have 0.1524 molar NaOH, and we're going to place that in a burette. And when we place it in the burette, we have an initial reading of 0.55 milliliters of base. So this is exactly where it's starting on the top of the burette. Now, keep in mind, burettes are all about how much are you dispensing. So if the volume starts at 0.55 milliliters, that doesn't mean you only have 0.55. It's where the label starts. So when you perform the experiment, the endpoint reached, now what the volume says is 33.87 milliliters. So we dispense from 0.55 to 33.87. So what is the concentration of HCl? How do we go through a problem like that? That seemed a little confusing. What should we do? So let's go through the steps, exactly what we need to do here. So the first part of this is that we need to predict and balance the problem. Okay, so that's always the first thing, right? So being that we had HCl plus NaOH, well, we're going to do inside outside. And I showed this one before, is that Na is going to bond with Cl, so cation always first, and then H with OH to make water. And it's already balanced with a 1-to-1 ratio. So it's a double replacement with the following products. Now, the main reason we're writing this balance equation is because we need to know the mole ratios for these problems. This one up here is a 1-to-1 reaction, meaning all the coefficients are 1. But sometimes it's not the case, right? You might have 2s and 3s or 4s, and that's going to affect your math. Now, the next thing is we need to stay organized and write down all the key terms. So with this, right, we were given the following problem, which had a lot of information in it, which was a little overwhelming. So what we want to kind of do is go through this and kind of highlight what is important. What do we know? So the first thing is that we had about 20 milliliters of HCl. So let's write that down for ourselves off to the side. So we have 20 mLs of HCl. Now, what else do we have? Well, we also were given the concentration and the starting point and the end point of our sodium hydroxide in this reaction, right? So we had the concentration here, which was 0.1524 molar, and we also have the initial and the end point of volumes as well. So let's write all these little values down. So with that, right, with our base concentration, we had for sodium hydroxide, so we had 0.1524 molar. Then we had a final volume of 33.87 and an initial volume of 0.55 milliliters for both of these two values. So what we are going to do is the first thing is we are going to follow our stoichiometry process when we're going to look at these. So we want to stay organized and follow our mole map. So let's do that for ourselves. The first thing we're going to do is we're going to follow our mole map. So meaning that we need to kind of map out the pieces that we have. So when we do solution stoichiometry, we want to go from the volume of the base to moles. Now, the reason we're going to start with our base is because we know the concentration and the volume. You always start when you know both those pieces of information. Now, with titration, we need to calculate what the volume is, though, in this case, because if you notice, we were given two different volumes, which is where we started and where we ended. So what we will do is we're going to calculate the change in volume, which is always known as the volume dispensed. So how much is used in this reaction. So we will just do final minus initial. So 33.87 minus 0.55 milliliters. And this is going to be how much volume we are going to have in this problem. So when we do the math, we're going to have about 33.32 milliliters at our disposal. So that's how much we used. Now, what we are going to do is we're going to start with the given term that's by itself. As you can see with this milliliter value, it's a term that you can't flip. It doesn't have a denominator. So we are going to start with that value and then use molarity to convert it to moles. So when we have 33.32 milliliters, we're going to convert this to liters first. So we have 1,000 mLs is 1 liter. Now we'll use our molarity, which was 0.1524 moles per liter. Okay, and that's of sodium hydroxide. Now what we are going to do here is we need to go to moles of acid. So this is where the chemical equation is useful, right? It's a 1-to-1 ratio, meaning that we have 1 mole of NaOH is equivalent to every 1 mole of HCl in this problem. You need to write that step down because your units need to cancel. All right, so we have 1 mole NaOH, 1 mole HCl. So now when we convert this, what we are going to end up getting is approximately 0.005077968 moles of HCl. But the thing is, we want to know the concentration. So what do we need to figure out concentration is, well, you got to remember, it's M is equal to moles over liters. And we were given the volume of HCl that was used, which was 20 milliliters, which is approximately 0.020 liters, right? So when we divide those two numbers, what we're going to end up getting is a concentration of 0.254 molarity as our answer. So that's what the unknown concentration was of our chemical in this case. So we do moles over liters is equal to our concentration, which is how we solve a titration problem. Let's go on to one more example. In a titration, if 20 milliliters of sulfuric acid is neutralized by 0.200 molar sodium hydroxide with an initial burette reading of 5 milliliters and a final reading of 65 milliliters, what is the concentration of the acid? Okay, so the first thing we need to do is we're going to predict and balance our chemical equation. So being it's inside out, we'll take sodium and combine it with sulfate. So we'll have Na, and then we want to write the plus here, and then we'll have sulfate, which is SO42 minus. We're going to drop their charges. So the 2 of the sulfate is going to come down next to sodium to balance out the pluses and minuses. And then we're going to be balanced. Then we're going to have H plus and OH minus coming together. So we have H plus, OH minus. Now these are technically just water. So we're going to keep it as HOH to help make balancing a little bit easier in this problem. So the first thing is that when we are looking at this is we want to start with usually the polyatomics, but right now your polyatomics are balanced. So we have 1 sulfate on the left and the right, and then we also have 1 OH on the left and the right. So what we are going to do is let's start with sodium, being there's 2 on the right, so we need 2 on the left-hand side as well. So now that we have that, we are going to look at the hydroxides. So there's 2 on the left and only 1 on the right-hand side right here. So what we will do is we're going to put a 2 next to HOH. And as a result, we look now at the hydrogens. We see that we have 2 on the right, and we also have 2 on the left. Everything is now nice and balanced, so we can kind of clean up our problem. We can rewrite H2O, and now we have a completely balanced chemical reaction. All right, so now the first thing is we need to stay organized when we are writing out this problem. So when we are looking at this, generally we want to write down all the little piece of information that we have when we are seeing this. So the first thing is that we have 20 milliliters of H2SO4, and we also have a concentration of 0.200 molar NaOH. So, and there's also initial and final volume readings. So we need to figure out how much sodium hydroxide was used. So when we're doing this, we ended with 65 milliliters was our final reading, and we started with 5 milliliters. So we're going to subtract those two numbers, and we're going to see that we had 60 milliliters of sodium hydroxide that was used in this problem. So that's going to go with sodium hydroxide. So when we're staying organized, this is always the crucial detail that we want to do when we are doing this, because it's going to make our problem easier when we are doing our molar map. Now let's go to that. So the first thing is we want to map out the problem. So we got to start with our volume because it's a term by itself. So 60 milliliters, we need to convert this to liters in order to use our molarity. So being that our goal is always the mole. So being that we have 1,000 mLs to 1 liter, this now puts our units primed to be able to use molarity for our conversions. So we have our molarity, which is 0.200 molar NaOH. So what we'll do is we'll put moles of sodium hydroxide, and that's equivalent to every 1 liter. We want to now use our mole to mole ratio, which, as we see, this is when balancing does matter. We have 2 moles of sodium hydroxide is equivalent to every 1 mole of sulfuric acid. So this is where it does play an impact in our calculations. Now, what we're going to do with that is we're going to figure out the number of moles. So what we will see is we'll get 0.00006 moles of H2SO4. And what we now need to do is divide this by the volume, which was 20 milliliters. So convert that to liters, so 0.0200 liters. And we will get a molarity of 0.300 molar H2SO4. That's our answer. Okay, so it's a little involved, but the hardest part is kind of the end part. You stop at moles and then divide it by liters. But I have a follow-up question to this. So what is the H plus concentration in this sulfuric acid solution? So one thing to keep in mind is, for a lot of you, is that you'll have new notation thrown at you all the time in Chem 3A. And one of the biggest things is square brackets. So if you ever see square brackets around a number, so just like this H plus here, where you see the orange brackets, well, this is referring to concentration, meaning molarity. So what is the H plus concentration here? So being that we have 0.300 moles over every of H2SO4 over every liter, we can do a quick little easy calculation based on dissociation. So being that H2SO4 is a strong acid, it's very soluble. So that means that we have 2 hydrogens that dissociate for every sulfate ion in solution. So we can label them as aqueous. So that means that we have, for every 1 mole of H2SO4, we have 2 moles of H plus ion that are created. So what is our concentration here? Well, it's going to be 0.3 times 2. So you're going to get a concentration of 0.600 molar for your H plus ion. Okay. So that is your answer here. So you can convert it for individual ions too, which is a very valuable skill to know, especially as we start to get closer and closer to understanding acid-base reactions and solving for pH, which is all about how much hydrogen ion there is in solution. All right, so this is the end of titrations and molarity. Thank you so much for listening. If this video helped you, please let me know. If it was a little confusing, reach out and please message me, comment below, and tell me all about it. If this is your first time here, please hit that like button, subscribe button, or refer to any of my other videos to help you try to pass chemistry. And thank you so much for listening. I'll see you all later. Bye now.